and I'm going to do a quick down and dirty travel down the rabbit hole, how you take stuff that you type with ASCII notation on a keyboard, how it affects actual hardware things. So this is going to be embedded systems, microprocessors, and code. So we're taking all of the levels where something you write in software physically affects hardware and causes it to do a thing. Because you know that's actually what's happening when you write code. You're physically manipulating electrons and stuff. Pretty exciting. Okay, so first I'll just start with a handful of quotes that I found interesting from interesting people. Programmers are tools for converting caffeine into code. I learned that during computer networks when at the 6000 level I had to learn Java. It was not fun. If you lie to the compiler, it will get its revenge. This is more true than you'll ever know, and it's written by the guy who wrote the library of regular expressions, which, when you need regular expressions, you will owe him a portion of your life. It is one of the most useful libraries in code that exists. Good judgment comes from experience, and experience comes from bad judgment. This is a fancy way of saying that you're going to make mistakes. You should learn from them. And then there are only two industries that refer to their customers as users, and that is software and drugs. So, if that tells you anything about the software industry, be careful. Okay, so embedded systems. What's an embedded system? I have a couple here. This is actually the TIFA board that if you are in embedded systems, you're playing with. This is another one from Cypress that I got and played with. What are they? They're just a dedicated computer system inside of a larger system that has usually a function. Like, it has a specific function. Modern embedded systems are based around microcontrollers. Some are around FPGAs, where the FPGA is simulating or hardware-coded a microcontroller. So it's essentially the same thing, but there is a distinction. A microcontroller is just a system on a chip or a small computer containing processor, memory, and programmable I/O. So this is essentially you take your huge computer and just stuff it into a single chip package where you have clocks and inputs and outputs, and inside of this there is all the stuff that's inside your CPU, just a little bit different, smaller. A central part of any microcontroller is the CPU, and this is the electronic circuitry that actually does the operations, whether they're arithmetic, logic, control, or I/O operations. They range from 4 to 64 bits. They're experimental ones. They go all the way up to 256 bits that we haven't found a use for them yet. It wasn't that long. I can remember in history when I started college where they said that it was insane. 64 bits was insane and we're never going to use it. And now everybody runs 64-bit microprocessors. It just happens. So, central processing unit. Memory. There are two kinds of memory. There's the volatile memory, which is RAM and registers and stuff like that. And this is, if you lose power, your memory's gone. And then there's non-volatile memory, where it persists after shutdown, and this is read-only memories. This is your CDs, your floppy drives, erasable, programmable ROM, electronically erasable ROM, and flash memory, so like flash drives and stuff. When it loses power, you can put it back in and get your stuff back. You use the peels in Digital Lab, if anybody's in Digital Lab so far, or when you get there, if they're still using peels, I don't know if you will be, but they're a programmable, non-volatile memory. Programmable I/O, this is the interface between the microcontroller and the outside world. And as I put up here, it's as simple as a single pin that's giving you a high or a low or an analog voltage out. to as complex as bus communication. So this is, you plug your USB into a thing, and it's doing high-speed gigabit data transfer and stuff. So programmable I/O is really kind of the essence of why embedded systems are a thing, because you have this, it's doing something and communicating to the outside world, and it does that with I/O or input-output. I'm not going to go deep into these two pictures, but if you have a microprocessors class and they don't talk about these two pictures, it's probably not a very good class. This is how all the pieces work together. And there's two basic principles. There's some variations of both of these out there in the real world, but there's the Harvard architecture and the von Neumann architecture, and there is, like I said, microprocessors as a class dedicated to these type of things. So you should see these again. And if you don't, you should come find me, and then I'll teach them to you. But what are the microprocessors made of? So if I have this thing, the microprocessor's here, what is the microprocessor made of? Well, the microprocessor is made of gates. And since I don't just have gates lying around, I have these other chips that have gates built into them. So this one is a green dot. This is a AND gate chip. Specifically went and tried to find an AND gate, and we'll talk about why this is difficult here in a second. But yeah, so inside of that is just a bunch of these, and that's how you do all your logic. So now you're stemming this with a voltage, a signal of some kind, and you get a truth table value out. So if A and B are the same, you get a voltage out. If they're different, you don't get anything out. But with all things, especially in engineering, it's not really this easy. Because of how we make stuff with MOSFETs and stuff. It's really these gates. So if I go back one slide, we had the AND and the OR, which are gates that you'll use in Boolean logic. And everybody, like discrete math and digital lab, you'll go over stuff like this, AND and OR using Boolean logic, and get deep down the hole with the Morgan's law and kind of switch them around. But really what we have is this, when you make them with actual transistors. We have the NOT, which just inverts. Exclusive OR, which is kind of complicated and takes up a lot of space, so you don't really see them all that often. NANDs, which is the most common gate, next to NOT. NOTs and NANDs are kind of where it's at. And then NORs, which is NOT OR. So how do we make this? Like, what is a gate made of? You get smaller here. What's a gate made of? Complementary metal oxide semiconductor, CMOS. There's positive doped and negative doped, which is P-type, N-type. Metal oxide semiconductor field effect transistors, and I have a handful of them right here. These are obviously discrete ones. They get much, much smaller than this. When I say there's several millions of these inside your CPU, I'm not talking about this size. I'm talking about the smaller ones. But so these are these, which can be put together to make these, which get put together to make these. So it's like Lego pieces, going all the way down to the bottom. So we have PMOS and NMOS. And how do we do that? So we have the gates to MOSFETs. So we had this NOT gate. This was a NOT gate. And if we were to make it, it takes two transistors, one P-type and one N-type, and you have the voltage, and depending on what the value is here, the value out here is different. So for a NOT gate, if you put in a positive, you expect to get a negative out. You put in a negative, you expect to get a positive out, right? From 1 to 0, back and forth. So if I put a 1 here, then this gate gets activated, which lets VS go through. If you put a 0 here, this gate is activated, which is VD. So if I put low here, high comes through. If I put high here, low comes through. So what's that? Here's the NAND, but it takes 4, where your inputs are A and B, and your output is the NAND of A and B. And for the sake of time and our brains, this is as far as you will normally go until you get to solid state physics. So we're going to stop here. Because solid state physics is where weird stuff starts to happen. And I don't